Climatology has moved beyond simple correlation. The IPCC's sixth assessment report peels away the chaos of planetary weather to calculate the exact mathematical certainty of the human fingerprint on global warming. To understand the math, we have to look at the baseline. By 2019, atmospheric carbon dioxide reached a concentration higher than at any point in the last 2 million years. The climate system's reaction to that carbon load is remarkably fast. The rate of global warming measured since 1970 has no parallel within the last 2,000 years of paleoclimate history. This chart maps that anomaly. 2,000 years of flat paleoclimate temperature data ends with a severe, near-vertical spike from 1850 to 2020. Climatologists apply calibrated terminology to this climb. Terms like extremely likely are rigid thresholds built on millions of data points. The synthesis of those probabilities was the Working Group 1 Physical Science Basis Report. The report's primary utility lies in its precision, calculating exactly what fraction of that thermal energy is strictly human-engineered. That calculation relies on a core metric called radiative forcing. This is the precise measurement of energy entering the climate system from the sun, minus the energy escaping back out into space. Isolating this metric is difficult. The Earth is a noisy system, flooded with internal variability, solar cycles, and volcanic eruptions that constantly shift the energy balance. The methodological achievement here is the use of multiple, overlapping lines of evidence to filter out all of that natural background noise. What remains is only the artificial forcing data. By deconstructing the mechanics of historical warming, scientists can now project specific, localized atmospheric outcomes into the future. We start with the observed net global surface warming. According to the data, the planet has warmed exactly 1.07 degrees Celsius since the pre-industrial era. This chart breaks it down. The black bar is the 1.07 degree total. The red bar shows greenhouse gases generated up to 2 degrees of warming. But human-emitted aerosols act as a cooling agent, dragging temperatures down by 0.8 degrees. Researchers also calculate the exact contribution of natural Earth cycles. The total impact of solar variations, volcanic eruptions, and internal climate variability is an effective net zero, sitting tightly between -0.1 and +0.1 degrees. The 1.07 degree reality we live in is an artificially suppressed number. In truth, the underlying human-driven thermal engine is operating with much more intensity than the baseline average implies. The global mean surface temperature is a mathematical abstraction. Nobody lives in a global mean. In reality, thermal absorption is highly unequal. Solid land masses heat up 1.4 to 1.7 times faster than the ocean surface. The disparity is even sharper in the north. Due to Arctic amplification, the polar region is warming at more than double the global average rate. This map shows how the IPCC tracks these divergent realities. By breaking the globe down into specific reference regions, the data reveals dense clusters of statistically significant heat extremes localized over human populations. Because energy distribution is fundamentally uneven, focusing on a smooth global average conceals the highly volatile physical conditions happening on the ground. The physics of these regional extremes follow a strict mathematical rule. Heat effects do not scale linearly. Every half-degree increment of warming causes exponential leaps in localized extremity. Look at this baseline thermal map at 1.0 degree of warming. When the average pushes to 1.5 degrees, thermal intensity spikes. Pushing to 2.0 and 4.0 degrees triggers compounding effects, resulting in an aggressive crimson saturation across formerly temperate zones. This heat alters the water cycle in very specific ways. The IPCC distinguishes between colloquial dry spells and meteorological drought, which is strictly defined as a pure lack of rainfall over a specific period. But the heat also triggers agricultural and ecological drought. In these events, extreme surface temperatures drive severe evapotranspiration. This strips soil moisture from the ground, causing drought conditions even if local rainfall remains constant. Preventing these half-degree increments has very little to do with stopping general warmth. It is entirely about preventing these localized feedback loops from collapsing regional soil and water systems. To model the remainder of the 21st century, the simulation engine uses a framework called Shared Socioeconomic Pathways, or SSPs. These pathways are not predictions of human behavior. They are rigid, heavily structured boundary conditions used to test exactly how the atmosphere must respond to specific emission timelines. This graph plots 5 divergent paths. SSP 1-1.9 charts net zero ambition by 2050. Conversely, SSP 5-8.5 maintains high emission trajectories. But the short-term reality is fixed. Regardless of the curve, breaching the 1.5-degree threshold is highly likely within the near-term window of 2021 to 2040. The physics of the next 2 decades are practically baked in. However, the atmospheric reality of the late 21st century diverges based entirely on the socioeconomic inputs established today. The terminal temperature reached at the year 2100 is strictly a mathematical function of the timeline required to reach net zero carbon dioxide. Reaching net zero halts the warming trend. If the global temperature overshoots the 1.5-degree target, achieving net negative emissions is the only mechanism capable of pulling that temperature back down. The precision used to isolate the human forcing signal in the historical record is exactly what allows researchers to map these future timelines. That isolated human signal directly generates the boundaries of every future spatial projection. Earth's internal variability has been mathematically overtaken by human influence. The broad physical trajectory of the next century is increasingly well understood. It is a direct response to our current policy pathways.